Welcome back to INST 314, Statistics for Information Science. I'm your host, Shawn Janzen. And in the previous videos, we started talking about different distributions you might experience, the normal distribution, which is going to be central to most of this video portion here, and we then introduced you to the concept of z-scores, where we can standardize observed values and find their probabilities underneath the normal distribution. In this case, topic 7.4, we're going to extend the conversation into confidence intervals and calculate those, and see how we can use confidence intervals in the context of statistical testing. So let's go ahead and get started. So when we're talking about confidence intervals, let's conceptualize what is a confidence interval. So the idea is that you want to know how sure you are of getting a particular point estimate based only on information from your sample. We can use the central limit theorem, which we're going to talk about in a future video, to help us generate an interval which we can be confident about where the true population parameter lies. You don't need the central limit theorem specifically to calculate a confidence interval, but explains why we can go ahead and use it. So confidence intervals are a range of values, the definition, a range of values we are fairly sure that the true value lies within. And we can use it to circulate in sample populations. It gives us an estimate of the population mean, and we typically express it as a percentage, such as a 95% confidence interval. So think of this such as an example that we're getting into election season soon enough, and you might hear a pundit say that politician X has a 60% chance, has a 57 to 63% chance of being elected. That is an interval. The pundit says that somewhere between 57 and 63% is the chance that this person might get elected. And so this person is assuming the true percentage by which that politician is being elected is somewhere between 57 and 63. That's the idea of a confidence interval. We're not certain where it is, but we're using our best analytical guess, if we want to be using that particular term. We're using our best educated guess to see that the true population average is going to be hiding within our interval. So some things I want you to keep in mind under your hat, that there are wrong ways to talk about confidence intervals, and make sure that you learn these quickly so you don't embarrass yourself when you get out to do analytics. Now, 95% confidence intervals are not interpreted as saying that there's a 95% chance that the true population is inside the interval. No. What we are saying by the definition of a confidence interval, we are 95% sure that the true population parameter is in the interval. 100%. 100% sure that the interval is going to be in there 95% of the time. It is not 95% chance that the interval is in there. It is not a 95% probability that we're going to say it is or isn't there, 5% chance it's wrong. No. What we're saying is if we do this interval with different samples, 95 times out of 100, we will get the true population parameter inside of our interval. That's what that 95% means. So how can we go ahead then and interpret some of this? Well, the idea is that if we went and sampled this many times, which I sort of just mentioned, we're saying that you're going to create different confidence intervals, and that 95% of the time is that you're right. Now keep in mind, this is true because the population parameter is fixed. There's some true value out there, whether it's a percentage or a mean or whatever it is that you're measuring, and we aren't assigning a specific probability to it. It is a single fixed value. And all we are saying is that we have some sample data and we're trying to estimate, is the population parameter in there, given what we know about the sample data. If we were going to put this out visually, what we have here are 20 different samples, and all of them are in blue would be the 95%, or 19 out of 20. And what we're saying is that there could be one red sample out there. Just by dumb luck and chance, that we could get a sample where we are the red sample in this case, and our sample is not going to contain the population parameter. The population parameter mu in this particular graphic is donated by the black dashed line cross-cutting vertically where mu is at. So we're seeing that in all of these blue samples, the blue line is the range of potential values in the interval. The blue dot is the mean or center of that interval, and we're saying that somewhere in that interval is the population parameter mu. And in the red one, we didn't make it inside the interval. 1 out of 20 or 95%. So again, just keep in mind, this little graphic is just supposed to kind of be a little fun for you to kind of remember that with any given interval, we may have a sort of whisker. Some intervals are going to be longer than others, and just implies a particular amount of trust. The smaller the amount of a whisker, the more the main body of data falls within the main distribution, and the more you could have some confidence in it. Now, when we want to go ahead and calculate these intervals, here's how we go ahead and do it. You have to start with alpha. Alpha is going to give you the probability that you're wrong. It's that maximum level of risk. And so in this case, if I have an alpha set to 0.05, I'm building a 95 confidence interval. If I convert the percentage of the confidence interval to a probability 0.95 and I add it to alpha, I sum to 1. If I take a alpha 0.05, turn it to a percentage of 5%, add that to a 95% confidence interval, I sum to 100%. Can you maybe see how these are sort of, again, two halves of a coin? They sum to 1 or sum to 100% together. So what we're then saying is if we use an alpha of 0.05, we're willing to be wrong 5% of the time, which is that flip side of a 95% confidence interval. So let's go ahead and find a z-score associated with a given level of alpha. So if alpha is 0.05, and we're looking at a two-tail proportion here, we could place half of that probability in the lower tail and half of it in the upper tail of the distribution, in which case it is 0.025 on one side and the other. So we can substitute these values into the equation where you have the confidence level is equal to your sample mean x bar plus and minus, because we're going to have to get two sides of the interval, the z-score you're looking at, in parentheses the standard deviation divided by square root of n minus 1. So let's go ahead and see some of this in practice. If we're building out a confidence interval for a mean, we could say that we've got a random sample of 178 households, and they have an average viewing time of 6 hours per day, and with a standard deviation of 3 hours per day. Use an alpha of 0.05. Well, if I take a 0.05 and I build out a two-tail hypothesis, then that splits my alpha to 0.025 and 0.975. That's the probabilities at the left and the right-hand tails of the curve. Those both correspond with a z-score of 1.96. Negative 1.96 on the left, positive 1.96 on the right, which is where we get that plus or minus 1.96 that we are going to plug in to our confidence interval formula. Now, we said that the average TV viewing hours was 6 hours per day, so we're going to plug that into where x bar was. We said the standard deviation is 3 hours per day. We're going to plug that into where the s was for standard deviation. And the sample is 178 households. That's going to become n. So what we have is the confidence interval equals 6.0 plus or minus that z-score of 1.96 times 3 over the square root of 178 minus 1. When we go ahead and process the math, we end up getting a confidence interval of 6 plus or minus 0.44 hours per day. So when we want to go ahead and state this, we would estimate that the households in this community watch on average 6.46 hours plus or minus 0.44 hours of TV per day. If you put that into an interval, we will minus 0.44 and add 0.44 to say that households on average, we would expect them to watch with a 95% level of confidence between 5.56 and 6.44, and that the population parameter mu is somewhere in between there. And so then what we're saying is, if the sample statistic is as much as plus or minus 1.96 standard deviations, that's that z-score, from the mean, that the sampling distribution, the confidence interval, will include the value of mu. And that only 5 times out of 100, that's our alpha 0.05 kicking in there, that only 5 times out of 100 will the interval not include mu. Right? In this case, 95% confidence interval. So how can we do this if we do it for proportions? Different formula, same concept. So we set our alpha, we find the z-score associated with it, and then we substitute in the information that we have. So in this case, the formula says that there's a confidence interval equal to the proportion of the sample plus or minus the z-score times, this is where it gets a little bit different, the square root of the proportion in the population times 1 minus the proportion in the population divided by n. Now, the little weird thing about this is p sub u, which is our proportion of the population, we often don't know it because we don't have, if we're not given population information, which most times we're not, what we're going to do is set it to 0.5. That is going to maximize the value we're going to get in the formula and give us the most conservative estimate. Why 0.5? Well, like I was just saying, the population proportion is unknown. So by trying to make the largest value we can for it, we're going to be the most conservative in our estimates. So think about it this way. P sub u is in the numerator, and the larger the numerator, the larger the error the estimate is that we're going to have. So if we try to maximize the size of P sub u, we'll be doing well. And in the numerator, it was P sub u times 1 minus p sub u. So I have out here a little math graphic, and I have different ranges from 0.1, where a pu could take a value of 0.1 to 0.9. And then I have what is 1 minus p sub u, and what happens if we multiply them together. And if we look on the horizontal black strip where we have p sub u times 1 minus p sub u and find the largest number there, we get 0.25. 0.25 corresponds with having a pu of 0.5. And that's why we use 0.5 in there as our default. Now let's go ahead and use a brief example here. If 42% of a random sample of 764 people from a Midwestern city are Republicans, what percentage of the entire city are Republicans? And when we do the math, don't forget that we have to change the percentage to a proportion, and we're using an alpha of 0.05. So we go ahead and take that proportion, we change it into 0.42 plus or minus 1.96. Why 1.96? Because we're using an alpha of 0.05. We chop it in half because we aren't concerned with the left or right side, and we go ahead and use the same probabilities as before, which was a z-score of negative 1.96 and positive 1.96. And then we go ahead and plug in to those parentheses with the square root. I said that our p sub u is going to be 0.5. We'll plug that in. And then underneath, in the denominator, we have n, which is 764 people in our sample. We go ahead and do the math, and it breaks down to 0.42 plus or minus 0.04. And so then we can go ahead and take it back into our context, changing those proportions back into percentages for our explanation. We can estimate that the city has 42% plus or minus 4% of the city's residents are Republicans. Or we can say that somewhere between the true population proportion is going to be between 38% and 46%. And that's with having an interval that we have a 95% chance that it's not going to include p sub u. So 5 out of 100 times, we're going to get a proportion for the city's Republicans that is not between 38 and 46%. Now, if we want to go ahead and do this in R, we have a formula that can help us with this, and it's called prop.test. Prop.test, and we can replicate the entire formula. We can do the entire formula by hand, just like we did on the previous slide, or we can do prop.test. And the way it works is you do prop.test, inside there, open another set of parentheses, and put the proportion you're working with times the sample size, close it, comma, sample size. And it will go ahead and run a test, and it's going to give you, inside the output, a spot that says 95% confidence interval, and you can see there that our 95% interval here is 0.3848, and goes, is the low value, and then 0.459 and keeps going for the high values, which round to approximately the 38 and 46% that we had before. And with that, I'm going to go ahead and wrap up confidence intervals, and I'll see you in the next video.